Recording is rolling. It's Wednesday, March 26th. So yesterday, actually last 2 days, we've been doing energy review. This is the last thing you guys saw yesterday. There's an elevator being pulled up. This acceleration, this velocity, this mass of the elevator. So what's the power? Oh, okay.
Good morning. My name is Roland Coglin, and I'm a member of.
All right, and we're back. So question was, what's the power of the motor at the top of the elevator shaft pulling up the elevator? So we've got to follow that up. I'm going to go into a momentum review with you guys today. Momentum impulse. You guys remember collisions or about whenever we see collisions, we're going to do that type of review today. Also, fill you guys in a little bit on what's going on in my other classes. My other classes, we're moving on to electricity and circuits. I got these breadboards with all these resistors plugged in. I got a bunch of Christmas lights. I got different batteries that are different voltages, like 1.5 volts on the AA and 9 volts for this boxy looking one, 5 volts on the cell puncher. So we're doing electricity. Now, I do want to do electricity and circuits with you guys, but it's just not on the AP exam, and we got a pretty good flow state on this review. So one day, next couple months, need to do something there. But we'll do a little bit with you guys. I got two guys painting the fence here, and that's the same math to solve this question with two guys painting the fence. It's the same math as solving resistors in parallel, which is like these Christmas lights tied together. And so we'll solve this one too. But first, let's do this elevator question. Okay. So who solved this between yesterday and today? Who knows how many watts? More than that. 60,000? Yeah, you guys get 60,000? Who's got 60,000? Yeah, 60,000 watts. 60,000 watts. That's what I got. 60,000 watts. Okay. So what's the power? Right. I gave you guys all these numbers into yesterday. Okay. Now the okay. Main way I'm thinking to solve this is, guys, power is what divided by what? Yeah, work over time. Right. It's a rate of energy transfer. Right. Work is energy transfer in joules. Time is in seconds. Joules per second gives you so many watts. Right. Okay. Now this particular question. There's a way you can rearrange this formula to answer a question like this. Because you guys know work is equal to what times what? Force times distance. Bam. So that could also be true, right? Okay. And then you could collect these variables differently. So, guys, what is distance over time? Yeah, speed, velocity, right? Force times speed, force times velocity, right? Is that true? Okay. So you can use this to answer this question. Okay. There is a tricky part on top. Actually, I've seen AP ask pretty much this exact question in the past. I don't know about these exact numbers, but pretty much this one is what is the force to pull the elevator upward? Now, if the elevator is being pulled up at constant velocity, would the force to pull it up be equal to the weight of the elevator?
Yeah.
Yeah, same magnitude. But if it's accelerating, is that still the case? No. Here, this elevator is accelerating upward, which means which force is bigger, the tension force up or the weight down? Tension force up. And that goes back to this elevator physics. Isn't that this right here? Okay. Now, actually, guys, get a look at the poster. This is something we reviewed before spring break. This could be a free response question. You could be expected to derive that entire page right there as a pre-response, and that might be like a bunch of points right there. Okay. So the takeaway though is that okay. Now here I put normal force like read from the scale, but this could be a tension force. Okay. You could cut straight to this, which is mass times g plus a, if you know the acceleration of the elevator, which is what I gave you, right? Or if you know the normal force on the scale or the tension rating, you could back calculate what's the acceleration. Okay? But you have to derive this if you're asked on a pre-response question. Okay? Okay, so here's the elevator accelerating down, not accelerating, or accelerating up. Okay, so let's go ahead and plug this in. So I know that this tension force and this cable. Now, if this was an FRQ, I'd want to derive this from scratch, but if this is multiple choice, I might be able to pull this equation in my back pocket. I'll go m times g plus a. Okay. And the mass of the elevator I gave you is 1,000 kilograms. Okay. Now G, I didn't explicitly write G, but you can make a reasonable guess. I'll use 10 meters per second squared, or if you do 9.8, it doesn't really change the answer a whole lot anyway, because we've got an acceleration of 2 meters per second squared on top of that. Okay. All right, is that true? Okay. So 10 plus 2 is 12 times 1,000. Isn't that like 12,000? Guys, 12,000 what? What's the unit right here? Guys, everybody look up here. Guys, everybody look up here. Look up here. Look up here. You're about to get a big old AP exam in a couple of months. What's the unit right here? Newtons. Newtons. Okay. So that's the tension of the cable. Okay. All right. Now we can plug that into here because that tension is a type of force. Just multiply by the speed. Okay. Got the answer. So let's go. Power is force times speed. So we got 12,000 newtons. It's going at 5 meters per second. Yeah, that's 60,000 watts. That's the answer, 60,000 watts. Okay. There's another way to write that with a prefix. Guys, that could also be called 60 what?
Kilowatts.
Kilowatts. Aha. Same thing. 60 kilowatts. All right, you guys good? With the elevator? Yeah, you guys with the elevator. All right. All right. So let's do this question of these guys painting a fence. Again, this gets a little bit to electricity because now all these circuits I'm doing in my other class, maybe I'll do with you guys one day. Yeah, we're doing this circuit. But if you have, say, circuits in parallel like this, okay. So if I tie the leads together on these Christmas lights, it's the same thing. Actually, this is this pretty much. Okay. Like what's the equivalent resistance? And it's the same math as if a bunch of guys team up to paint a fence because they're working in parallel. So same concept, same math. So say it takes Alan 3 hours to paint the whole fence by himself. And Bob, well, it would take him 4 hours to paint the whole fence again by himself. But they're going to team up and make a two-man team. So how long does it take them as a two-man team? Does anybody know the answer to that or how to solve it? 1.7? Aha, yeah, it is 1.7. 1.7 hours. How'd you know it was 1.7 hours?
I gave like a number to the fence and then gave them a rate change and added the rate change per hour.
Ah, okay, yeah. So yeah, so say okay, there's some amount of fence. Right, there's like rates that they're painting the fence. Hold up, okay. Oh, I'll show you guys the math how to solve. I'm gonna kind of cut through some logic how to solve it and just cut straight to the math how to get. So you can do it this way. 1 over, yeah, there's different ways to think about it, but I'll show you guys the fast way. 1 over the total time is 1 over Alan's time plus 1 over Bob's time. So 1 over the total, and we're solving for the total time. Actually, I meant to say something else. Let me back up a little bit. Ooh, okay. I meant to have you guys frame the possible answer. Like even if you didn't know exactly how to solve this, you could kind of hone in on possible answers. Oh, for example, guys, what if it's 2 Bobs, like 4 hours, and his friend also takes 4 hours? Then together, the answer would definitely have to be what? 2 hours, right? Could be half the time. Right? Or what if it was 2 Allens? How much time? An hour and a half. Okay. Well, if we have 1 Allen and 1 Bob, doesn't the answer have to be somewhere between 1.5 and 2 hours? Right? It comes out to 1.7, but how is it? All right, so let's finish this up. So you can do 1 over Allen's time, which is 3 hours, plus 1 over Bob's time, which is 4 hours. Okay? Now, what's the common denominator? 12. So 4 over 4 here, 3 over 3 here. So 1 over the total is 4 plus 3 over 4 times 3, which is like 7 over 12. Therefore, the total time, yeah, just reciprocal, 12 over 7. Of course, that would be hours. I haven't written the unit yet, but just know the hours, which is like 1.71 hours, which is between 1.5 and 2, isn't it? Right? Somewhere in that window. Okay, good. All right. How about a couple other things on this? Do you guys see a shortcut that comes out? Like if you had lots of pairs of friends over and over and over, and like one guy's 1 hour, one guy's 6 hours. Right? You kind of see a shortcut that falls out of the math. Guys, everybody look up here. Guys, everybody look at this. So do you guys see that at the end of the day, just with 2 friends, it's always going to be the product over the sum? You guys see that product over sum? In this case, 4 times 3 over 4 plus 3. Okay. Now that shortcut, product over sum, here, I'll write that down. So product, which is 4 times 3 over sum, 4 plus 3, only works with 2 people painting the fence, or it could be like 2 resistors in parallel. Okay. What if there was a third friend? So what if we have a third friend, Chad, that helps paint the fence? Could you do 1 over the total time is 1 over Alan plus 1 over Bob plus 1 over Chad? Do you think you do that? right? And what if you have more friends? Can you do plus 1 over Derek, plus 1 over Eric, plus 1 over Ferric, and just like keep going, right? And what if you have like 50 friends? Could you just do 1 over, right? So you can have like 50 friends and just keep use this reciprocal method.
Get it done in 1 second.
Yeah, right. It's like everybody's like, hey, done. Yeah. But the product over sum only works for 2 friends at a time, right? Yeah. All right. A little bit of what we're doing in math class, but I think that's a good one to know before you graduate anyway. All right, let's do some momentum and impulse. Okay. So, guys, what is momentum? Momentum is what times what? Yeah, mass times velocity. And is that a vector or a scalar? A vector, right? So last couple of days we've been looking at energy, which is a scalar. So direction didn't really matter. Like if you had atwods and one block was moved down and one's moved up, the direction didn't really matter, right? But now we're back to direction mattering. And what scenario do you know to apply this feature? Collisions. Yeah, whenever you see collisions, you know that this mass times velocity for the whole system is going to be conserved in a closed system. Right? It's going to be conserved. Right? And the fact that it's a vector value means if someone's going to the left and someone's going to the right, you have to sort of subtract them from each other, right? Because they're opposite directions. Right. Here's real generic conservation of momentum. Right. So notice this is all in 1 dimension. I think it's all AP ever asked, right? So not really glancing collisions, right? But they're just okay. So it's all on the x-axis, right? You've got this mass velocity and this mass velocity, and you add them up before the collision, right? And notice, guys, would these both be positive, or would one be positive, one's negative? Yeah, one's positive, one's negative, and you know that because they travel in opposite directions, right? So they sort of subtract from each other. Right? In fact, they might possibly even zero out, right? If you've got like 5 units to the right and 5 units to the left, that would be 0 momentum in the system, wouldn't it? Right? That could possibly be the case. Okay? Maybe you have something that's kind of like this. It's like, you come to a stop if it's inelastic. Right? Right? And then after the collision, well, if they bounce off each other, then the momentum is conserved after the collision too. Right? Oh, now they could bounce off each other a bunch of different ways. Oh, they might bounce off each other really nice, boing. And what kind of collision is it called if they bounce off each other as well as they possibly bounce off each other? That's elastic. Yeah, perfectly elastic, or AP just is elastic. Right? If they stick together, that's perfectly inelastic. Right? And a lot of times AP just uses the term inelastic for anything other than perfectly elastic. Right? So if they something like half deflated tennis balls, something like that. Okay. So let's do a perfectly inelastic collision. Let's do a calculation here. So what if I give you mass A is say 5 kilograms, mass B is 3 kilograms, velocity A initial is like 10 meters per second to the right, velocity B initial is let's say 5 meters per second. Okay, so I'll call this to the right, I'll call this to the left. So right and left, just like my picture shows. Okay. So you guys calculate, and I'll also calculate at the same time. What is the post-collision velocity? Right, that's the question. This right here. Right, so everybody go ahead and calculate that. I bet on the AP exam they're going to ask you this exact question. Right, what's the post-collision velocity? All right, I got the answer. Who else got the answer? Yeah, what you got? Huh? Ah, all right. Cool.
To the left.
Huh?
35 to the left.
I don't think that fast. Guys, can the post-collision velocity be faster than either of the original ones was originally moving?
No.
No, nothing's going to speed up. Okay. Right. So, I know Alex told me he got it. What? It's slower than that. Okay. Who else is going to get this? That's really, really close. Huh. Okay. I think Hans got it. All right, who else got to get this? Guys, you guys are doing conservation of momentum, right? Nathan got it. Guys, conservation of momentum. You guys just told me momentum, mass times velocity. Right? It's all conserved. And if they stick together like that, perfectly inelastic, they have the same post-collision velocity. Jack got it. Okay. So, yeah. All right, so some of you guys got it. All right, here's the formula you guys should use. Well, here's the framework. Momentum is conserved before and after. So if I add up all the mass times velocity that's before the collision, and then after the collision, they have to equate. That's conservation momentum. Right? In this case, they're going to make one giant mass with some common final velocity because they're stuck together. That's perfectly inelastic. Okay? So let's just pop some numbers in. You got MAVA naught. So that's 5 kilograms at 10 meters per second to the right. I'll call right positive. Okay? And then plus, and they got 3 kilograms moving at, 5 meters per second to the left. Should I call that negative 5 meters per second? Okay. And then after collision, now if this was a free response question, I would definitely write this step. I write sum of P before equals sum of P after. Okay, so that might be a point itself, just that's it. Okay, I'm just head straight to the numbers. I got 5 kg plus 3 kg. Okay, one giant mass moving at some common final velocity. It's a vector, right? These are vector values. Get a little arrow of that. Why not? Okay. And that's what we're solving for. Are you guys okay with that setup? It falls straight out of that math. Okay, you guys good with that? All right. So how much momentum? I got 50 units of momentum here. I got negative 15 here. Guys, what's 50 plus negative 15? 35. So I got 35 units of momentum, kilogram meter per second. And that's going to result in 8 kilograms moving, not fast in what direction. Okay. So divide over 8, and you should get V final equals 4.375, maybe meters per second. And the fact that it's positive means it's overall going to the right. Okay. Yeah.
If you didn't write going to the right on your answer line up or two, would they mark it wrong?
If either implied or specified that to the right was the positive direction and your answer was positive, then yeah, they would give credit for that. Yeah, they should. Okay. Okay. Another little detail here is, guys, do you actually know this level of precision, like down to the thousandth place? If my significant figures are like only 1 or 2 sig figs, come out. So if this was multiple choice, they might just say 4.4 meters per second. Okay, if there's multiple choice, they probably say 4.4 meters per second. Okay. All right. Okay, next one. So, guys, what's the opposite of perfectly inelastic collision? Perfectly elastic. Okay, that's the next one coming up. And to give you guys a visual, it's not like perfectly bouncy balls, which, okay, I think this one's out of alignment. Yeah, best demo ever. Yeah. Yeah, well, I should have bought the slightly more expensive one, but yeah, string rope. Okay. So perfectly elastic. Okay. Now, guys, you're probably going to get one reference to a perfectly elastic collision somewhere on your exam. Okay. You could be somewhere in the NCQ, could be somewhere in the FRQ. They usually don't have you. Well, here, I've seen elastic like 1 or 2 different ways. But you have to know what are the conditions for perfectly elastic. Guys, what's one condition? Yeah, kinetic energy is conserved. And the other condition, of course, is what else is also conserved? Yeah, momentum conserved. But momentum conserved regardless of the type of collision. So that's always true. Okay? But this right here, yeah, here's your special condition that makes it perfectly elastic, perfectly bouncy, is that kinetic energy is also conserved. So that's all your 1/2 mv squared bits, which are, of course, are all scalar values. Okay? So you got vector values here, you got scalar values here. But you have this giant system of equations. Okay, this giant system. Yeah.
Ignore the fact that in the Newton's cradle points potential energy by going.
Right, because yeah, Newton's cradle. Right, if the ball's like swinging, like changing height. Right, that's not part of the collision. Right, so then when it comes back down, that potential just turns back to kinetic, and it gains the same speed it did when it while it was started.
Right before the collision, all of its energy is kinetic.
Yeah, right. It's just moving like horizontally at that moment. It's all kinetic. Yeah. There you go. All right, so there is a solution to the system of equations, which is this gold box here. You would not be expected to memorize that. Alright, so guys, here's the two questions I've seen APS in the past about this, and you're probably gonna get one or the other of these. Right? If it's multiple choice, they'll probably give you multiple choice answers and say, which of these multiple choice answers represents an elastic collision? And the best way to handle that, do you guys remember seeing this before maybe in a practice? There, guys, focus here, okay? Is to go through the multiple choice answers one by one, so start with option A, and run these equations and see which ones validate both of these conditions, right? Unless you just want to memorize this gold box, that's okay too, you can do that, right? And especially this kinetic energy condition, right? Maybe especially focus on that one, right? And if you get like 35 joules on the left side and 35 joules on the right side, then you know it satisfies that particular condition. Okay? And then that's probably going to be the elastic collision. Okay? The other way I've seen elastic collision be incorporated, and this has been in some FRQs in the past, is one small step of a larger puzzle. So they might have something like, oh, there's a ball that rolls down an incline and it slams elastically into a stationary ball. And they'll specify that they're both the same mass. And what the outcome of that, you're about to see it right here. Because guys, if they're the same mass and it's elastic, then and one starts at rest, then what happens to the ball that slammed into it?
Stops.
Yeah, it stops. And it transfers all its momentum and all its energy into the other one. Is that true? Right? As long as they're the same mass and it's perfectly elastic, you guys just saw that right there. Right? So that might be part of a large one, right? Maybe one rolls down an incline, slams into this one like turns into a projectile and flies off the tabletop and something. Okay, so that might be like a connecting step. Okay. All right, what else we got? You guys did some labs. You guys remember those collision carts? Okay, there's different things you can do with the collision carts. We know that. Here's a pretty good one. Right, so types of collisions. Got a whole spectrum here. Oh, if okay, so for a general, let's start right in the middle here. So for this general collision, momentum is always conserved. Right? And guys, what happens to kinetic energy in general, just in general for most collisions? Does kinetic energy due to a collision tend to increase or decrease? Decrease, tends to decrease. Okay, tends to decrease. That's why post collision is going to be less than pre collision. Right? And this there's it could possibly be equal, but it's only going to be equal if it's what? Perfectly elastic. Aha, that's this one right here. Right, that's why it's greater than or equal to here. Right? Because it could be this elastic. Right? But if the two objects stick together, the kinetic energy always does what?
Less than.
Yeah, always decreases, right? It's always less after than before, right? Okay. Now there is one more I threw on this table, which is the reverse of a collision, which is explosion, right? Which might be maybe, oh, there's someone on ice skates, which gets rid of all the friction between the person and the ground and throws a snowball, right? Sometimes you'll see that version too. That could also be a version of this last one. Okay. So momentum's still conserved. Right? Oh, did I play you guys a Magic School Bus clip?
Yeah.
Yeah, it's like through the baseball on the frictionless baseball field. That was also a version of this one. Momentum was conserved, right? And in that case, what happens to kinetic energy after compared to before?
Greater.
Yeah, greater after compared to before. Because that energy comes from somewhere. It comes from, like if you throw the ball, it comes from your muscles. If it was a grenade, it comes from the chemical reaction.
If you had two equal mass hockey pucks on the frictionless table and you had one was at rest and you threw the other one at it, would that hockey puck that was in motion would it stop?
Wait, so sorry, so what?
You're talking about Newton's cradle, how if they're the same mass and it's a perfectly elastic collision, then the one that was in motion stops. Would that apply to like a hockey puck?
Okay, so you're saying if one hockey puck starts at rest and the other one comes and slams into it? Okay, yeah, if it's perfectly elastic, yeah, it would look just like Newton's cradle. This one would stop and this one would go. Yes, that would probably be the case. It would probably make it elastic. Yeah. And guys, what if this was inelastic? What if one hockey puck comes and slams into another one and they stick together? Like if this one comes in at 10 meters per second, then how fast would they slide off together if they stuck together? 5 meters per second, be half the speed, right? Okay, so it depends what kind of collision's going on.
What race?
All right. This next one. Oh yeah.
An explosion. It's when you have two objects together and then the kinetic energy is transferred into one of them and it shoots off.
Okay. Yes. So for this explosion one, like, where does this energy come from? Is what you're saying? Right. Okay, so if it's a grenade, all that energy was stored in the chemical bonds, like a chemical reaction. Okay, right. Oh, if you say like throw a ball on an icy surface, then that energy was in your muscles. Right. So those are like non-mechanical forms of energy. Okay. But then they become mechanical, right? Because they go into the motion of the object. Okay. Okay. Impulse. Guys, I got a graph here, which is force versus something. Guys, if it's an impulse graph, it's gonna be force versus what? Force versus time. Here, guys, put your phones away. Phones away. Phones away. Okay. Guys, on the AP exam, are you going to see some graphs that are force versus time? Yep, they're gonna show up. And what's the question probably gonna be when you see it? Yeah, it's probably gonna be impulse. And what property that graph would lead to the answer? The area under the curve. Now, if it's a constant force, you'll get like a rectangle shape. You also pretty commonly see a triangle type looking graph. And the idea is like this. Like if a bat hits a ball, and you're just focused on the ball. So maybe this could be a graph that just focuses on the forces on the ball. Okay? Then the bat makes contact with the ball and then pushes against the ball, and the ball starts to reverse direction, and then the ball leaves the bat here. Right? And this whole time interval might be like 100th of a second or some tiny fraction of a second. Okay? Right. Oh. And so here you go. Oh, impulse, which is the change in momentum. Now, usually the mass of the object is constant, so it all goes to the change in velocity, mass and change in velocity. You get that by force times time interval. So average force times time interval. We'll do an application of this one. Well, it is. Yeah, I think I got some other posters. So, okay. All right, let's do. You guys good with this so far? Actually, I'm gonna shuffle posters around a little bit. All right, because I remember a specific application of this one I like a lot. You guys remember the ball bouncing off a wall? Okay, let's solve a ball bouncing off a wall. So, say I give you that right there. So I'll give you guys this picture. Okay. Let's have the mass of the ball be about 3 kilograms. Let's have this initial velocity. Well, let's just say velocity. Let's say the velocity doesn't change. Let's say the speed doesn't change, I should say. Right? The velocity changes because the direction changes. But let's say the speed is the same. Ball's going to bounce elastically off a frictionless wall. So I'll just call it V. So the speed, let's make it about, let's go 50 meters per second. Okay, in a boing. Okay, so that's really, really fast. But let's say that the time of contact with the wall is like 0.01 seconds, so 100th of a second. And let's take this angle right here, theta, and let's make that 60 degrees. And which is pretty close to the picture. Okay. You guys got all that set up? Okay. And so, okay, give the rest of the title. So this is bouncing elastically off a frictionless wall. So the speed post-collision is the same as the speed pre-collision, same speed, boing. Okay. And the question I have for you guys is, what is this force from the ball? Okay. Oh, by the way, what kind of force is that? Like, it's not a tension force. It's a what kind of force? Normal force. Aha. And normal means what again? Perpendicular. So that, of course, always had to be perpendicular to the wall. Okay. So what is that force equal to? Okay. So I'll solve it. You guys solve it. I've got the equations covered up, but see if you guys can get that anyway. Right, so we're going to get here. All right. I think I got the answer. All right, how about you guys? Anybody got the answer yet? This is what? Yeah, the mass of the ball is 3 kilograms. Yeah. Yeah, it's a 3 kilogram ball. Ah, Hans got it. All right. Hans for the win. Yeah. So what what I got was almost 26,000 newtons, okay, which I think would make sense because, well, isn't this ball like 3 times as massive as your biggest lab weight? Okay. And 50 meters per second. I think that's faster than Nolan Ryan can throw a fastball. So, yeah, that'd be a pretty big force. So let's do some vector analysis here. I got this is coming in at 50 meters per second. There's a velocity vector. Okay, so V equals. Okay. And I need to break this into component. Actually, well, let me break it this way. Okay. So the ball is kind of going towards the wall, but it's also kind of traveling parallel to the wall at the same time. Okay. And this is 60 degrees. Then how fast is it traveling straight towards the wall? What times what? 50 meters per second times what?
Sine.
Aha, sine is 60 degrees. Aha, that is it. Okay, let's see what is that? 50 sine 60 degrees is, yeah, 43.3 meters per second. Okay. Now, guys, the force from the wall, this normal force from the wall, does it change its motion parallel to the wall? No, it only changes its motion like towards away from the wall. Okay. So this component right here, you don't even have to calculate, you just ignore that. Okay. Although cosine 60 is half, but that doesn't even matter. Okay. Okay. Because post collision, the ball keeps traveling the same speed in that direction. Like if you just follow the ball, like how fast it's going parallel to the wall, it never changes. Okay. But towards and away from the wall, ooh, that radically changes. Okay. And since this is bouncing elastically off a frictionless wall, then you can say that this is also 50 meters per second here. And what is this component also equal to?
42.
Yeah, 43.3 meters per second. Okay. Except that now, instead of towards, it's away. So maybe I should also throw a negative sign on that, right? Because it changed direction too, didn't it? Okay, so, right, so here's your, well, if you cross multiply the time interval, doesn't that become the impulse equation? Force times time interval is mass times change of velocity. Right, divide the delta t down, right? Which, by the way, also looks a lot like Newton's second law of motion. Does this look like F equals ma? F equals ma? Yeah, right. A lot of teachers actually teach impulse equation, and Newton's second law is basically the same thing. Okay. So let's plug some values in. So the force from the wall, the normal force, is the mass of the wall. So I got 3 kilograms. Times the change of velocity. Now, change of velocity. Here, you guys tell me, what should I write for the change in velocity? Aha, 86.6. Aha, because it's 43.3 minus 43.3. Or sorry, minus negative, I should say. Minus a negative. Meters per second, meters per second. Okay. And then this is all divided by the time interval. So the collision happened in 0.01 seconds. Okay. So I think that should do it right there. Okay. So let's do 3 kilograms times 86.6 meters per second is the change velocity divided by 0.01 seconds. Look at, yeah. So 26,000 newtons, or you could say 26 kilonewtons. There you go. Yeah, Ash.
Is there an equation on the sheet that you can derive the F equals M and change it in order?
Yeah. All right. So where is it on the on this page right here? The AP equations. All right. So it's right down here. It's right near the bottom. Right. You got forces change of momentum over change of time, which is equal to m delta v over delta t, which is F equals ma. Right. So it's all squeezed right there. Right. And the line right beneath it. Oh, that's also called capital J. I haven't seen that in many years, but AP just made this page new a few months ago. So capital J also they call impulse. Okay. Sometimes you see that. Okay. Yeah, it's right near the bottom. Right. Oh yeah. Okay. All right. What's next? Okay, so So we did that, which is really an example of this. That's all good. Ballistic pendulum. Yeah, let's do a ballistic pendulum. I think we got time. So this one's fun. Oh, this could be a pretty extensive free response question. Okay. Here. Actually, before we do that, I do want to do one of these with you guys, but let's hang tight on that one. Right. Let me show you guys some other posters first because these other ones a little easier. Right. Right, so relationship between kinetic energy and momentum. Guys, what's the formula for kinetic energy? 1/2 mv squared. What's the formula for momentum? mv. You see they have the same basic ingredients, right? They both got m, they both got v, right? Kind of different concepts, but so if an object has one of these properties, then it should also have the other. If it has kinetic energy, then one will have momentum, vice versa. Okay. So what's the connection? So I did a derivation here. Got momentum is mass times velocity, okay, therefore, wouldn't velocity be momentum divided by mass? Right? Think of it that way. Right? Then you can substitute that into this expression, kinetic energy 1/2 mv squared. You guys just told me that. So you can take this p over m, substitute in for that v right there, and isn't that going to get squared? Right? And then now this m is squared on the bottom, and there's one m on top, so that partially cancels, but not completely, right? Okay. So that's how you get this here. So kinetic energy is p squared over 2m, or you could also solve for p, and you could arrange and sort in terms of k. Okay. Now, I've seen in the past for FRQs, if an AP grader is scoring an FRQ, I've seen this as not something you would be necessarily expected to know, but that you might know, and that if a student writes this, they'll give you credit for it, and they'll say, "Oh, it looks like the student really did that." So it's kind of extra. Like if I guess if this class is kind of easy, and you've got extra space in your mind to memorize some new things, then that could be pretty good, right? And then this green box is the rotational version of that. So if you have like a bowling ball rolling, like that. Okay. All right. What else I got here? Closed and open systems. So what makes the system closed in terms of momentum? If momentum is what conserved, so some momentum before equals some momentum after. Okay. In terms of forces, what made a system closed? If there's no external force, no external force. Yeah. And in terms of energy, if there's no work being done, right? So there's 3 different perspectives on what makes a system closed, right? No external force, no work being done. In this case, momentum is conserved, right? So if a system is open, there could be an external force. There could be work being done in terms of energy. And in terms of momentum, you could say there's a what? Like an impulse, like a change of momentum impulse, right? Because these would all be momentum terms, wouldn't they? Mass and so kilogram meter per second, kilogram meter per second, kilogram meter per second. Okay. So an impulse would be a change of momentum. Right? All right. So we look at that. I got some that are pretty similar here. Right. This concept, got poster just for this concept, is this is going to show up on the AP exam in some form, one way or another, right? Some version of the story. Suppose you have 2 asteroids in deep space. Or you might have like 2 ice skaters or some version of this. It's always the same thing, right? Where there's some kind of collision. Now, what kind of collision? I don't know. Maybe they stick together. Maybe they bounce off each other. Maybe it's elastic, inelastic, something in the middle, right? Doesn't matter. This principle still applies. Is that if you just focus on not either asteroid, but the center of mass of the 2 asteroid system, or if it's 2 skaters, the center of mass of the 2 skaters, right? Or if it's 2 collision carts, the center of mass of the 2 collision carts. Okay. You will never actually know when the collision happened if you just focus on the center mass. Right? You just watch the center mass and it's like, I don't know when the collision happened. Okay, you guys hear that? Okay. That's true for elastic and inelastic. That's true for one-dimensional collisions, which is probably what all you get anyway, but also in 2 dimensions and 3 dimensions, right? If you have like billiards going on and you just focus on the center mass of the 2 balls, you'll never know when the collision happened. That is also true for, say, like if somebody throws the ball. So here's the magic school bus question, right? So a pitcher throws the ball, right? And if you start off on the mound with the ball at rest, what's the velocity of the center of mass? It would be 0, right? And then if you throw the ball goes to the left and you scoot off to the right. What's the velocity of the center of mass? Still 0. It's still parked right on top of the pitcher's mound, isn't it? Right there, right? So I got 0 momentum ever in that system. Right, and then you could use this, I think we did solve this, didn't we? So if you know the mass of the ball, if you assume the mass of the pitcher, and you know the speed of the ball, if you calculate the speed that you're skating off towards second base, you do that too, right? Okay, so yeah, like that, pretty basic stuff. Okay, and one more that's pretty related to all this is grenade explosion, say projectile explodes. So what if I throw a grenade and explodes in midair, and now I got like 1,000 grenade parts, or maybe 2 grenade parts if they simplify it and want you to solve for something. Okay, but if they ask something like, where does the center of mass of all the grenade parts land? Would the answer be the same as if it had never exploded at all?
Yes.
Yeah, right. As long as you ignore air drag, which we always do in this class, yeah, that'll be true.
Because they still have momentum.
Right, all the parts still have right individual momentum. Right, even if one shoots kind of backwards, that means that the forward ones shoot even more forwards, and it all cancels out. Yeah. So at least yeah. Right. Oh, and speaking of center of mass, here's how you calculate center of mass. You take a weighted average. So if mass times location, all divided by the sum of the masses. Okay, so for 2 masses, it would be like this. Okay. Be the point you could bounce on your finger. Be the point where if you spin it in the air, it would spin about that center point. Okay. And then the momentum version of this is if you very simply change this x to a v for velocity and just put these objects in motion, would that equation still be valid? Yeah. So that'd be like center mass from a momentum point of view. All you do is change this x to a v, right? And then mass and velocity. Right. All right. So let's solve a ballistic pendulum. Right, so you guys can do this whole process here. I'll just throw some numbers at you guys. Actually, what we got, like 4 minutes? Well, yeah, okay. I don't think we have time to solve this whole thing, but I'll walk you guys through it. Okay. So just conceptually, and show the math here. Okay. So here's the scenario. I fire a bullet into a block. The bullet embeds in the block. And the whole thing swings up to, well, there's going to be some height change, and it's going to swing back. Okay. Now, there's different variations on this, and there's different questions you get asked. But the classic setup is that the bullet embeds in the block. There's a variation where it goes through the block. And the classic question is usually what's the firing speed of the bullet, because that's kind of the purpose of this. Okay. It's kind of easy to measure what's the height change or what's the angle that it swings up to. But it's maybe kind of hard to know how fast does this bullet fire, especially if it's like 1880 or something, right? So you guys see I got 2 blocks set up because this is a 2-part process. And if you know either the height change or you know this L and this theta, which by the way, guys, if you know L and theta, can you solve that height change? Can you guys do that? Okay. I got a poster just for that too. Let's see if let's see, I have that in the energy section, so I can find it real quick. Here it is. Okay. That's some geometry. Okay. So could you guys do this geometry? I know haven't you guys seen this like 20 times already? Okay. So this height change is equal to the length of the string minus this L cosine theta. And you can factor in L if you like, and it looks like this L times 1 with cosine theta. You guys see that? Okay. Okay. So if you're given L and theta, you could calculate the height change. AP would probably give that to you. Okay. Right. And you have to solve this backwards. So if you start from knowing the height change, you work backwards to figure out what was the original firing speed of the bullet. So from this height change, that's what part of physics are you going to use to figure out how fast was it moving at the bottom? Energy. There's conservation of energy. Okay? And what type of energy do the block and bullet have together at the bottom? Kinetic. And at the top, they have all what? Potential. So kinetic turns to potential. The masses all cancel. And oh, look at that. No surprise. The close collision speed is equal to square root 2gh. Okay. Oh, yeah.
Are you assuming that the block just stops?
Yeah, the block would come to a stop up here. Yeah, because it's on maximum height. Yeah, this is really H max. Right. And then it just swings back and forth for a while. Yeah, so that's the maximum height. Okay. Now that's the first half of this whole setup. Because I still don't know the firing speed of the bullet. I just know how fast I got the block moving post collision after embedded. Okay. So to go back and calculate when the bullet embedded in the block, that means you're going to use what in physics? Conservation of momentum. Yeah, conservation of momentum. So let's do a conservation of momentum right here.
Inelastic collision.
Yeah, for an inelastic collision. Okay. Could you guys write the next step? Guys, here, last thing in your notes today. Can you guys write the next step in this process? So right here, write this equation you have to do to solve that. You guys follow this process so far? You guys, okay, what's going on? Okay, so forwards in time, all the momentum was supplied by the bullet. So that would just be your MV for the bullet, MV bullet, mass bullet, velocity bullet. Okay. And after the bullet embeds in the block and sticks in the block, you have one giant mass of the block plus the bullet,
Yes.
and it's moved at its own post collision velocity, right? V post, right? In fact, do you know what that post collision velocity would be at this point? Because that's what you solved up here. It's a square root TGH. Right? Just a substitute right there. Yeah. That's the firing speed of the bullet. Okay. All right. Ooh, that's a perfect stop point today.